All right, we'll get started here. Um, were there any questions? Okay. This week on Wednesday, I'm going to be out. Actually, Wednesday this week and Monday next week. And so I'll post a video, or I might have a remote, like a Zoom or WebEx class on Wednesday. But just to let you know, there's going to be no in-person class on Wednesday and Monday. Is that okay? You got it? This coming Wednesday? Yeah, and Monday next week. All right, so that's an important announcement. Number one. Yes, you have to fill that out. For the titration, yeah, you need the equation there. I wrote the equation, though. It's HCl plus NaOH for number 1. For reaction 2, it's different. All right, let's take a look at that for experiment 10.
Which number do we use to find the percentage of the acetic acid?
I'll talk about it tomorrow in lab. Yeah. You don't have to turn it in just yet. You can finish it. Turn it in later. You have to figure out it's a stoichiometry problem. You're supposed to figure it out yourself, given the hint. Did you find the hint in the procedure? They gave you a hint for solving that particular problem. Did you find it? And then you could figure it out using the equation for percent. What is the generic equation for percent? Oh, that's the percent yield. What is the percent composition equation? Percent composition. No, the percent by mass composition is, let me see if I have it over here. It's 2016. I'll just do it now. Or actually, let me talk about it tomorrow. It's lab stuff. So let's take a look at the schedule here. I'm sorry? Yes. Mass of A over total mass times 100. Exactly. That's the percent. So you need that equation, and then you just use a little bit of dimensional analysis. You can figure it out. Tomorrow we're starting experiment 11. And I'll talk about experiment 10 tomorrow. I need to catch up, though, because I haven't finished chapter 13. I need to finish up chapter 13. I'm supposed to be in 15 now. So let me do a little bit of catch up here. Well, I'm just about done. I didn't talk about organic. I need to talk about organic. We'll take a look at, this is an organic molecule here. Organic molecules are carbon based, except certain carbon-based molecules like CO2 and carbonate, CO3 2-, bicarbonate, we consider those inorganic. But for the most part, all the other carbon-containing compounds we consider organic, including ions. And the reason is is carbon chemistry is so rich. There's so many different types of carbon-based compounds out there that they had to make a separate field for just the carbon-based compounds. They wouldn't do the same thing for silicon, let's say, because silicon, even though it's in the same family, there's much fewer.
Are there any organic compounds that are not carbon-based?
No. No. So the reason why we have this separate field of organic chemistry is just because of the way carbon bonds. It can form up to 4 bonds, and it doesn't mind bonding to itself. Silicon can do the same thing, but there are only thousands of silicon-containing compounds. Germanium, only thousands, but for carbon, maybe millions, billions. I mean, more can be made, and people are making new carbon-based compounds, and people are finding new carbon-based compounds as well. And so, anyway, this is organic one. Is this polar or non-polar?
Non-polar.
It's non-polar. All the bond dipoles would cancel out. These are both trigonal planar carbons. This is chapter 13, the end, chapter 13. If you look at methane, methane's carbon, these are all organic compounds here as well. But some of them are polar, some of them are non-polar. This first one's non-polar. All the bond dipoles cancel out. These are carbon-chlorine bonds, which are quite polar. These are carbon-hydrogen bonds. Even though they're showing them as polar here, the difference in electronegativity is very small, and therefore we classify these as non-polar covalent. So even if the bond dipoles didn't cancel out, like in this last one, we'd still consider it non-polar. So you could have much more complex structures than this. As long as it just contains carbon and hydrogen, that is a hydrocarbon, then it's non-polar. And so these are like oils. Hydrocarbons are like gasoline, oil, etc. Here we have some polar ones where the bond dipoles don't cancel out here. You can see this. We kind of ignore the carbon-hydrogen bonds here and just look at the carbon-chlorine bond. That's going to tell us which direction the bond dipole points. So for organic CO2, this is considered inorganic, even though this is a carbon-based compound. It's just traditionally considered inorganic. This is non-polar. A lot of organics are non-polar. Water is quite polar. The bond dipoles do not cancel out in water. So when we look at organic chemistry, it's basically these carbon. Carbon has the, it says the right size and right strength of bonding. It forms 4 bonds. It likes to form 4 bonds. And so the strength of the bonds are strong enough that they can form stable compounds. Inorganics are basically the rest. And so like certain carbon-containing things like carbonates and oxides, carbon monoxide, carbon dioxide, and cyanide. Cyanide is, you could classify that as organic, perhaps, but typically I guess that's considered inorganic. Here. So we have different kinds of hydrocarbons. We have the alkanes. The alkanes are only single bonds. And so this is how you differentiate here, alkanes. And we have something called the alkenes and the alkynes. The alkenes will have a double bond, and the alkynes would have a triple bond. Alkynes is spelled with a Y. It's K-Y-N-E-S. And so we'll have something like this. This is one of the simplest alkenes. This is actually the simplest. This is called ethene. And if we have a triple bond, this would be the simplest triple bond compound. This is called ethine. Ethine has a common name, ethine, which is called acetylene. You don't have to know acetylene here. And then we have ethane. Ethane has no double, no triple bond. So what is this going to have is it's going to have two carbons that are going to have a single bond between them, and the rest of the bond's carbon. Note that carbon always has 4 bonds here. So when I look at ethane, this carbon has 4 single bonds. When I look at ethene, it has 1 double and 2 singles. When I look at ethine, it has 1 triple and 1 single. And those all count as 4 bonds, even though we can't separate them into 4 distinct bonds. So for example, ethene, we could separate that into 3 groups. And ethine, we can only separate that into 2 groups. So this would be trigonal planar, this is linear, and what would this be for ethane?
My water says it is alkaline water. Does that relate to that?
No, alkaline relates to pH. So your water has a pH that's kind of high. pH gives it a more slippery taste to it. And so there's a little bit of texture. So this is trigonal planar, this is linear. What is this in ethane? Tetrahedral. Tetrahedral, you have to get good at visualizing and drawing tetrahedrons. And so these are tetrahedral arrangements. And normally the way we do this is we do it zigzag. I either go down, I like to go down, but whatever you do, you should always draw it the same way. And so since we draw it like this is the way that we'll typically draw the wedge dash diagram. We draw it in a zigzag fashion like this. And so what I do is I have this go to the right so I can continue the chain. Carbon likes to form these chains. So if I have a 2-carbon chain, we call that F. 1-carbon chain, it's not really a chain, but just 1 carbon, we call that meth. If I have 3 carbons in the chain, I call it prop. And so what we do is we zigzag the chain like this. And so we could put like 20 carbons in a chain. We just keep zigzagging them. So this is 1, 2, 3, 4, 5. 5 carbons we call pent. This is 1, 2, 3, 4. 4 carbons we call bute. 3 carbons here, this would be called pentane. Not pent. Pent is 5. What would 3? Do you know what 3 is called?
Try.
No. Actually, this should. Actually, I need to erase this. When we draw this, we try to draw the tetrahedral structure. And in organic chemistry, you learn this. You spend some time learning to wedge the middle carbons in the chain like this. And so we wedge one out, wedge one in. They have the same perspective. So if the right one's wedged out, we wedge out the right one. If the left one's dashed in, we always dash in the left one, and then the chain continues like this. And then there'll be one more hydrogen. 3 carbons is called prop. And so this is called propane because there's no double or triple bonds. And so propane is very common chemical. It's just 3-carbon alkane here. And the drawing is like this. And so whatever we do, we have to be consistent. If you like to draw it going up like this, that's fine. You can draw it up like that, but we do it typically like this. It makes it easy to draw out like this. And we need to know the structures of these. We have other ones like this. This is called normal butane. This is called isobutane. Iso has this little fishtail here, called that. And so we have isopropyl alcohol. Isopropyl alcohol will have this little fishtail here. But this is called isobutane because it has 4 carbons. Isopropyl will only have 3 carbons in an alcohol. But isobutane here. This is normal pentane, so it's just a 5-carbon chain like this. This is isopentane, which has this little fishtail on the end. We call this little fishtail dimethyl kind of group here. This is neopentane, which is kind of this tetrahedral arrangement with these. These CH3 things on the end here, you see the little C with the 3 hydrogens? That's called a methyl. CH3 is a methyl. And so another name for this would be 2-methyl butane. Let's put that in here. This is called 2-methyl butane. This is called 2-methylbutane because it's a 4-carbon chain with a methyl group stuck on the second carbon. This one could be called 2,2 dimethyl propane. So the propane comes from the 3-carbon chain here. We have a 3-carbon chain, and then the 2, we have a methyl, and the 2, we have another methyl, so we call it 2,2-dimethyl propane. Neopentane is its common name, isopentane, those you just memorize, or neo, it kind of has the iso group. There is a systematic nature to it. The iso group is this little fishtail thing at the end, or usually, or in the structure somewhere. And so those are some examples of organic nomenclature. Organic nomenclature requires a lot of memorization. And so next we have alcohols and ethers. And these are structurally, these are a little different, so they're going to have a little different properties. They're all going to have this group, the hydroxyl group. The hydroxyl group is not hydroxide because this is covalent, not ionic. And so we could look at some simple alcohols. The simplest alcohol is going to be methanol. The meth means 1 carbon, so this is a 1-carbon alcohol, and there's no double bonds or triple bonds, so it's methanol. So meth is, we have the 1 carbon here, no double, so all singles, and then we have an alcohol attached to it. So methanol looks like this. The other name for this is called methyl alcohol, because remember the CH3 group is methyl. CH3 is not quite complete because carbon likes to form 4 bonds. And then we have the alcohol here, so we call this methyl alcohol. There are lone pairs here. There's a lone pair that's going to, actually I'll be consistent with the way they drew it, I think. I'm not sure how they drew it. We'll have 1 lone pair wedged out here and 1 lone pair dashed in here. So that shows the tetrahedral electron geometry around the oxygen here. We have the tetrahedral. Both of these are tetrahedral EGs, electron group geometries. But this one is tetrahedral molecular geometry. This one's bent at 109 molecular geometry. And so this is methyl alcohol here, or methanol. Now bute is 4 carbons. And so this would be butane. There's no double or triple bonds, and it's an alcohol. So this is butanol. This is normal butanol. Normal butanol has the alcohol at the beginning or the end. But we could have 2-butanol. 2-butanol would have the alcohol stuck on the second carbon. 3-butanol would have it on the third carbon. You would think this is 4-butanol, but it isn't. 1, 2, 3, 4. No, the numbering system, we try to lower it, name it with the lowest numbering system. So this would be numbered backwards. This would be carbon 1, this would be carbon 2, this would be carbon 3, this would be carbon 4. That way we put the alcohol on the lowest numbered carbon possible. So we'd have to number these in the reverse. So this is not 4-butanol, this is actually just normal butanol. If we had 2-butanol, I'd stick the alcohol on here. So I get rid of this, let's say I get rid of this hydrogen and then just put the alcohol on here like that. That would be 2-butanol. 3-butanol, I'd stick it here somewhere. It doesn't matter which one I pick, this hydrogen or that hydrogen. 4-butanol, I'd be back to the same. It'd just be normal butanol. So that's something that we keep track of in the numbering system. Now, these are ethers. Ethers have this bridging oxygen here. So this bridging oxygen here bridges 2, not methyl. This is methyl is 1, this 1 carbon. But if I have 2 carbons, that's ethyl. And so this is called an ethyl group. An ethyl group is a CH3CH2. So CH3CH2, and then it bonds to something. This is called an ethyl group. because it has 2 carbons. And so what this is called is di, meaning 2 ethyls attached to the ether. This is a diethyl ether, so I have these, and the bridging oxygen here. Over here I have methyl, which is the CH3 group, and this big group over here is called phenyl. This is what we call a benzene ring. This benzene ring is all sp2 carbons, excuse me, sp2, you haven't heard that. Ignore it. They're all trigonal planar carbons. Organic chemists call these sp2 carbons, and the tetrahedral carbons, organic chemists call those sp3 carbons. So this is sp3 carbon, these are sp2 carbons. Or this is a tetrahedral carbon, these are trigonal planar carbons here. You learned that in Chem 1A. But this is called methyl because we have a methyl on this side, and then we have a phenyl attached on this side, and this is an ether. Now, the ether, the bridging oxygen is actually a tetrahedral EG, because we have the lone pair here. So we've got 2 lone pairs here. So this is a tetrahedral EG and bent MG. It's bent at 109, but the 2 lone pairs are going to distort it down to about 105. But then you got these, what we call steric hindrance. You got these bulky groups attached here, which could cause the angle to widen as well. There's going to be some repulsion between the methyl and the phenyl group. Here, maybe not so much repulsion. The next group we're going to look at are the carboxylic acids. The carboxylic acids will have this structural, we call this a functional group. And the carboxylic, the COOH group, or CO2H, is called the carboxyl group. And the carboxyl group, the Lewis structure looks like this. We're going to have a trigonal planar carbon here. Should be Y. Actually, let me try to draw it a little bit more. So I was giving you guys grief on your drawings. Here, I'll try to be more accurate. So we got 3 groups, and those 3 groups will want to be at 120 degree angles relative to one another. And so we'll have this tetrahedral EG or EGG electron group here, electron geometry, but bent molecular geometry. And then this is going to be attached to something. We use the generic R for this. This is just the rest of the structure, rest of molecule. So R is going to be a carbon. It could be a hydrogen. If R is a hydrogen, then we call it formic acid. Formic acid is the simplest of the carboxylic acids. All the carboxylic acids are weak, which weak acids only partially ionize in water. And so we have, let's take a look at some simple carboxylic acids. The simplest is formic acid here. Formic acid, I don't particularly like this drawing here because the 2 lone pairs are not like 180 apart from each other here. The 2 lone pairs, one lone pair should be wedged out here, and another lone pair should be dashed in here to show more of a tetrahedral arrangement. In a tetrahedral, we try to keep the bonds in the plane. Keep the bonds in the plane and then wedge out this and dash in this. Way. Not always, though. Sometimes we'll put the lone pair in the plane. For example, in ammonia, we did the lone pair in the plane. But this shows more of the tetrahedral type arrangement. But when we look at the molecular geometry is just bent, because we don't look at the lone pairs when we consider the molecular geometry. So this is trigonal planar here on the carbon, both EG and MG, or EGG and MG. So this is called methanoic acid. Methanoic acid has a common name. It's methanoic acid because carboxylic acids all end in oic acid. And so we know we have a carboxylic acid when we see oic acid. And methane means just one carbon. And so this is a one carbon carboxylic acid, referred to as formic acid. So people just memorize that. This is called ethanoic acid, but nobody ever calls it ethanoic acid. Ethanoic acid is its systematic name. Eth, because of two carbons, ane, no double bonds. Oic acid, it's a carboxylic acid. So ethanoic acid, but everybody calls it by its common name, acetic acid. And so you'll never hear ethanoic acid. Basically, the R group is a methyl group in this case. And so we have a methyl group attached to the COOH here. And so CH3COOH is one way. This is called the condensed structural formula here. The condensed structural formula tries to give you a more accurate depiction of how things are bonded together. So we have a CH3 bonded to a COOH here. The O's aren't bonded to one another. You know, we got one O bonded to the carbon and another O bonded to the carbon. So this would be it. Propanoic acid, you know, we'll stick an ethyl group. But if we stick an ethyl group here, which is two carbons, then we have a 3-carbon chain altogether. So if we have 3 carbons, we call it prop. Prop, 1, 2, 3 carbons total. That would be propanoic acid. And then we have butanoic acid, etc. This is not drawn the way we typically draw it. You know, this is just a 3-dimensional structure. We could twist it around different ways. But if we were trying to draw this 3-dimensionally, we would have to have a more consistent, more systematic method of drawing it. Yes, Jason?
Like the OH at the bottom being the hydroxyl.
That's the hydroxyl group, but we don't consider it an alcohol. You know, we don't consider this an alcohol because this carbon double bond here changes the alcohol group significantly. So it kind of looks like an alcohol with a hydroxyl group here, but it has 2 groups. This carbon double bonded oxygen we call the carbonyl group, and the OH we call the alcohol. But when we have a carbonyl and an alcohol together on the same carbon, we call it a carboxyl group. So we could try drawing. We could drawing maybe like butanoic acid. So butanoic acid, we would start off with methyl on the end here. And then we're going to get 4 carbons in a zigzag arrangement like this here. And then these middle carbons, what we do is we write the carbon-carbon bonds in the plane. That means the carbon hydrogens have to come out and stick in. So here's our butane chain. There's no double bonds, so butane chain. But it's an alcohol, so we have to end it with COOH. So maybe what I'll do is I'll put the oxygen double bond down here, and then the oxygen single bond up here, and then put the hydrogen in the plane. So I can zigzag these all in the plane. That means this lone pair has to wedge out of the plane, and then we're going to have a lone pair that dashes into the plane like that. And so this is tetrahedral. We're just looking at molecular geometry. Tetrahedral, trigonal planar, bent, 109. And this would be called butanoic acid. And so what people do is they'll do this structurally. So we have a CH3 on the end, followed by CH2 in the middle, followed by another CH2 in the middle, followed by COOH on the right end. And so this would be the condensed structural. We call CH3 groups methyl groups, and these CH2 groups also have a name. Those are called methylene groups. And so this is a methyl group here. And the middle carbons in the chain are methylenes. And then we have the carboxyl group here. So bute, 4 carbons, ane, no double bonds, oic acid, carboxylic acid, butanoic acid. So what we did was we covered some functional groups. The functional groups are structures that have certain properties associated with those structures. So one is the alkanes. You know, the typical properties for alkanes are they're nonpolar. These are electron rich, so they're flammable. Fuels, usually. They're not acidic, not basic. They don't undergo metathesis. This is redox. Then we have the alcohols. Alcohols are also electron rich, but they're polar. They're polar slash nonpolar. Depends on how big an alcohol is, but the alcohol part itself is polar. You know. The ROH group. But the R group could be nonpolar. Quite nonpolar. These are also flammable. In other words, they're electron-rich fuels. The carboxylic acids, the ethers, we had the ethers. The ethers are mostly nonpolar. Or polar. Actually, they're polar, slightly polar. They're kind of a bridge, slightly polar. They're also flammable. A lot of organics are electron rich, they're flammable, they're combustible. A lot of the inorganics aren't so, except cyanide. Cyanide's, you can burn it, but CO2 not so much. Carbon monoxide, yes. The ethers. And then you have the carboxylic acids. Carboxylic acids can also burn, but not so well. They aren't nearly as electron rich as some of these others, but it depends on how big the carbon chain is. You know, the more carbons you have here, the more electron rich it is. What we do is we look at the oxidation states. So you look at the oxidation states, we see that these carbons are all electron rich. This carbon is not so much. But these are weak acids. And they're also fuels. Like a lot of people like the taste of vinegar. I was looking at the ingredients. Like I never knew. I never thought about what is barbecue sauce made out of. You know, do you know what the ingredients of barbecue sauce are? It's like,
Carboxyl acid.
yeah, there's some carboxylic acid in barbecue sauce. Barbecue sauce is like ketchup and vinegar. Didn't know that. So I like vinegar, the taste of vinegar. I like barbecue sauce. So anyway, that's organic. So in organic chemistry, you'd have to learn all the names and everything. For us, we're not going to bother memorizing the names. I just gave you a quick preview of what to expect. But I used to have people memorize it in Chem 4. Meth is 1 carbon. You know, we go just in order. F, 2, prop is 3, bute is 4, pent is 5, hex is 6, hept is 7, oct is 8, known is 9, dec is 10. So these are the parent chain. We can go beyond that, you know, to like dodeca, etc. So we're going to move from this chapter. A lot of people find organic difficult. They find it difficult. Do you know why? Because the amount of memorization you have to do. If you find memorization difficult, then organic's going to be difficult. If you find memorization difficult, you got to come up with some kind of system for memorization. And so try to come up with some system, because what I'm going to do is I'm going to do a retest for the nomenclature. The retest for the nomenclature is going to be able, is going to give you the opportunity to be able to recoup some lost points. So just the ones you got wrong on the other nomenclature, you can recoup some lost points from those. And so I'll give that later. Come up with some kind of system to memorize it, and we'll do a retest. Unfortunately, there is some memorization that you have to do in science. It would be nice not to have to memorize anything. The ideal gas law is pretty easy to memorize, though. So we're going to talk about the ideal gas law. We have the other laws, we have something called Avogadro's law. Avogadro's law is just simply this. The amount of gas, save this. So when we think about Avogadro's law, I just think the amount of gas in moles is equal to N. And this is directly proportional to the volume. So that makes sense. The more gas we have, the greater the volume. So if we take, is this Avogadro? This is not Avogadro's law here. Oh, this is Avogadro's law. Let's see, how many gas particles do we have here? 1, 2, 3, 4. So let's say hypothetically 4 gas particles occupy a volume of 50 milliliters. What if I have 8 gas particles? What would the volume be? If I have 8 gas particles, the volume would be 100. So 1, 2, 3, 4, 5, 6, 7, 8. So I have double the volume because I have double the particles. But you might go, how can that be? Because these particles are oxygen over here, and these particles are hydrogen. And hydrogen, aren't they smaller? The hydrogen atom is smaller than the oxygen atom, right? So how could it be that they occupy the double? Shouldn't it be less than double because hydrogen's so small? And it turns out no, it depends on the particles, the number of particles here, not the actual size of the particles, because gases are mostly empty space. And so, in other words, the number of particles is going to be directly proportional. The number of particles is directly proportional to the volume. So if 4 particles takes up 50, then 8 particles will take up 100. So if I have hydrogen reacting with oxygen, so in this particular redox reaction, oxygen reacts with hydrogen. We need twice as much hydrogen, so we'll have twice the volume. So if I have 50 milliliters of oxygen, I need double that in hydrogen. And then I'm going to make water. Okay, in this reaction, I'm going to make, if I take 4 of these and 8 of these, I'm going to make 8 waters. If I make 8 waters in the gaseous state, that's 8 gaseous particles. That's going to take up 100 milliliters, like this. So in the law of combining volumes, we come up with a simple equation like this. The simple equation that we come up with is this. 2 hydrogens plus an oxygen, gas. Normally we form liquid water, but in this case I'm going to go to gaseous water. This is very important that it's gaseous. If it's liquid, this doesn't work. Eventually we go to liquid. I'll just do it like this. Eventually the water cools down to H2O liquid. But the law of combining volume says this. If I take 2 liters of hydrogen, how many liters of oxygen will I need? 1 liter. And how many liters of H2O gas will I form? Yeah, I didn't balance it, did I? I'm going to form 2 liters. Here. So this is the law of combining volumes. The law of combining volumes, I just come up with these mole ratios or liter ratios, volume ratios I'm going to come up with. Volume ratios for gases. And so 2 liters of hydrogen gas for every 1 liter of oxygen gas, or 2 liters of hydrogen gas for every 2 liters of H2O gas, etc. So I can use these in stoichiometry. As long as the temperature and pressure are the same for all gases. It doesn't work for water, liquid water. So for example, I can't say 2 liters of hydrogen gas for every 2 liters of H2O liquid, because liquids take up a lot less volume. And so the actual volume of the liquid is going to be a lot smaller. We could figure it out, but I'm not right now. And so the law of combining volumes, this is like this for reactions.
So this would only apply to gases?
Only applies to gases. So it makes the stoichiometry very quick. So for example, let's say I had 50 liters of hydrogen. How many liters of oxygen will I need for this reaction? I can do it in my head. I don't have to have a drawn out dimensional analysis type problem. So if I have 50 liters of hydrogen, how many liters of oxygen do I need? 25. Do you see? You can do these calculations very quickly. 25 liters would be the stoichiometric amount. So this is it. This is 3 particles, takes up this volume. 6 particles, double the volume. 9 particles, triple the volume. In other words, if I have 1 mole takes up this volume, 2 moles would double, 3 moles would triple. We don't usually talk in individual particles because it's too much. So that's Avogadro's law. What we're going to do is we're going to combine the laws that we covered earlier with Avogadro's law. So we had Charles' law. We did the experiment with Charles' law. Volume is proportional to temperature. And then we had, actually, the Charles' law, I'm going to have you do one extra thing to that. So I'm going to give you back the Charles' law report, but we're going to do the plot over again in the back. Boyle's Law, you don't need to know the names of these, but we did this one also. We did the combined gas law. Now we're going to do the Avogadro's law and combine everything. When we do Avogadro's law and combine everything, this is what we end up with. This is the complete combined gas law. The complete combined gas law is P1V1 over N1T1 is equal to P2V2 over N2T2. This is equal to a constant, so this ratio is always equal to a constant. This constant we give a name to. This constant we call R. And R depends on the units that we use for pressure and volume. Since what are the units that we could use for pressure? There are a number of different units we could use for pressure. Atmosphere, PSI, bar, torr, millimeters of mercury, kilopascals, pascals, etc. And so R changes depending on what units we use. So what we do is we just fix the units. So what do you think the most common units are?
1 atom or atmosphere.
Yeah, 1 atmosphere. And so what we do is we fix R for it like this. And so this type of stuff, this is not even. This stuff, just ignore this stuff. This is the ideal gas law here. This is what you have to remember. Ideal gas law, some people call it the Pivnert equation. PV equals nRT. And so what we do is we just multiply both sides by RT here. Multiply both sides by RT, and we come up with this kind of thing. Somewhat, just rearrange things. So PV equals nRT. And so what we do is we do pressure in atmospheres, we do volume in liters, we do temperature in Kelvin, and when we do that, R is going to equal 0.08206 liters times atmosphere per mole Kelvin. And so we only want to memorize one. But your book uses many different R values depending on which units they use. And so my recommendation is just to memorize one and then convert everything else. So if we're in bar, we have to convert it to atmospheres. If,
It's mostly, I think, 62.4.
yes, right. In the homework, they like to use other units. So depends on what units they use, they keep changing the bar. I mean R. I do it the opposite. My approach is different. In the homework, they have a whole bunch of R values. Many, depending on units. I want to try to keep the amount of memorization to a minimum. Even though you have to memorize some stuff, what we want to do is we want to minimize how much stuff we have to memorize. And so you already have to memorize conversions. So for example, if we convert from atmospheres to millimeters of mercury, you have to memorize that. There are 760 millimeters per atmosphere. So we already have all these memorized. If you have milliliters, we need to convert it to liters. You know, if we have Celsius, we need to convert it into Kelvin. And so we already know these conversions, so we can convert things into atmospheres, liters, and Kelvin. And then just memorize one R. However, if you use milliliters, then we're going to have a different R value. If we use bar, we're going to have a different R value. And so I don't want to memorize a whole bunch of different R values and then use those accordingly.
It's the same
Liters, this one,
What is it?
times atmosphere, ATM, divided by mole Kelvin. And so in the book, you'll see, in the solutions guide in the book, they use lots of different R values, which,
I think it's just only two.
yeah, except they set up the problem all the same. So what if you have, let's say, bar instead? You know, do they give you the one for bar? Or what if you had, you know, gallons instead? Did they give you the one for gallons of gasoline? No. And so it's because they only used two, because they only gave you two different sets of units for pressure, volume, and temperature, but there are a lot more than two different sets, you know, and a mix of those two. So if you have it already memorized, that's fine, but I wouldn't bother. We can derive all the simple gas laws from the ideal gas law. Interestingly, you know, this is the case for a lot of things, like quantum mechanics. You know, the quantum mechanics is called modern physics. You know. But what about the old physics? The old physics, classical physics, Newton. So, you know, is Newton like Bohr? You know what happened to Bohr? What happened to Bohr theory? It's disproven. We don't even use it anymore. The same thing for Newton's laws. Newton's laws are all wrong. Therefore, we should just abandon Newton's laws and then just focus on quantum mechanics. Is that the case? It's not the case, because classical physics, Newton's laws, can be derived from quantum. So if we start off with quantum and we make an assumption, we assume that we're only working with large systems. Then what happens is the quantum mechanical equations simplify to Newton's laws. And so we don't have to memorize these individual laws here, because all these laws can be derived from the ideal gas law. You know, let's make some assumptions. So for example, Boyle's law, we assume that the volume and the temperature are constant. Charles' law, we assume that the pressure and volume are constant. And Avogadro's law, we assume that the pressure and temperature are constant. And so by making certain assumptions, we can derive these simpler gas laws. And so the only gas law we need to know is the ideal gas law. And so this makes our life a lot easier, because all we need to do is memorize one law, and that's it. We can also get the combined gas law. The combined gas law is something we don't have to memorize either. The combined gas law is, we just rearrange this equation. PV over NT is equal to R. R is a constant. And so no matter what or how we change this ratio, the ratio is always constant. So we could start off with one set of pressure, volume, amount, and temperature, and that's got to equal another set of pressure, volume, amount, and temperature. So we could change anything, but the ratio's got to stay the same. And so we can derive all of them from the ideal gas law, and so all we need to memorize is the ideal gas law. And so we could take a look at some examples here. A 0.1000 mole sample of helium is placed in a piston and heated to 25.00 degrees Celsius. The volume is adjusted to 4.600 liters, and the resulting pressure is measured as 0.5319 atmospheres. Use these data to determine the value of the universal gas constant. And so what we have to do is we have to come up with a table and see what they give us. In the equation, we need pressure, volume, amount, and temperature. And so the pressure we have is 0.5319 atmospheres. So 0.5319 atmospheres. So this is in the correct units, so we don't have to change anything. The volume is in 4.600 liters. 4.600 liters. So liters is correct. the amount of gas is 0.1000 moles, so that's also correct, 0.1000 moles, rather than grams, rather than number of particles. And the temperature is 298.15 Kelvin. So we have 4 sig figs, 4 sig figs, 4 sig figs, 5 sig figs. And so we just solved this equation for R. R is equal to PV over NT. And so we just plug in the pressure, 0.5319. So let's do that here. .5319 times 4.6 divided by 0.1 divided by 298.15. So I come up with this 0.08206,406. 0.08206,406. Units here will be liters times atmosphere per mole Kelvin. And then we're going to round this to 4 sig figs, 0.08206 liters times atmosphere over mole Kelvin. And so this is what you should memorize. Now our book only does 3 sig figs, but the problem with 3 sig figs is if you memorize it to 3 sig figs, you can grab those if you want.
That's
Okay. If you memorize it to 3 sig figs, you're going to have to memorize it again in Chem 1A, because in Chem 1A you need it memorized to 4 sig figs. So it's not that hard. 8206 for 4 sig figs. So save yourself some unlearning and relearning it. So they got it to 0.08206 atmospheres. I do liters atmospheres, but it doesn't matter. It's cumulative. The mole Kelvin. So applications of the ideal gas law. One of the applications is to solve it for a single variable. So they don't even give an example of this. This is like what we just did here. The unknown variable is R, and they give us the other 4. R is not a variable, it's a constant, but we made it a variable in this particular case. But if we were given 4 of the 5, we just use a little bit of algebra, then what they call it, plug and chug, plug the numbers in and then chug out the calculation. So this is called a plug and chug calculation. So this if all but one variable is unknown, then plug and chug. But there are other more complex applications. One of these is called the molar mass calculation here. It's not working. And so we can calculate the molar mass. I don't do it this way. Actually, I just don't like that particular way of doing it. Nor do I like this particularly that much either. But if you like it, that's fine. You do it that way. First off, what is the definition of molar mass? Yeah. Molar mass is defined as mass per mole. Mass is usually in grams, so it's grams, and then N is in moles, so it's grams per mole. Units would be grams per mole. So the molar mass, we're going to abbreviate MM for molar mass. Molar mass is equal to the mass over moles. But moles, we have to remember N. But N equals the amount of gas in moles. So what we can do is we can substitute that in here. So this is just going to equal the mass over N. Come on. So if we know the mass and we know the number of moles, then we could stop here. But if we don't know the mass and the number of moles, then we know this. N is equal to PV over RT. So I just rearrange PivNerd. PV equals nRT, divide both sides by RT, I get this. And so what this is going to equal is going to equal mass over PV over RT. And then this is going to mean that I'll flip this over and I'll get the mass times RT divided by PV. And so we come up with this equation. The molar mass is equal to the mass times RT over PV. But this means we have to know a lot more. Rather than just knowing the mass and the number of moles, we got to know more. We got to know the mass, the temperature, the pressure, and the volume. Which we can. And so we look for relationships. Well, one of the relationships that we might see here is mass over volume. Do you know what mass over volume is? Mass over volume would be grams per liter or grams per milliliter. What has a unit of grams per milliliter or grams per liter? Density. This is grams per liter. This is equal to the density of the gas.
Mass over volume, or is it density?
Density times RT over P. So these are different kinds of relationships that we can generate. So we could determine the molar mass if we know the mass, the temperature, the pressure, and the volume, or we know the density.
What is it in terms of gas again?
What's that?
And it's equal to the mole, but it's respect to gas. Why is that?
Because we usually use the symbol N just for gases only. It doesn't have to be. You know, I didn't have to write it as M. What else can we do? Likewise, we can rearrange this equation. To solve for the density. I'll do that. Or we can derive the density equation separately. So let's see this. What is the pressure in a helium helium-filled 0.77 liter balloon if it contains 1.0 grams of gas at 22 degrees C. So what do we have here? We know it's helium. We have the volume, we have the mass, and we have the temperature. Yeah. And so we need the pressure, the volume, the amount, and the temperature. We don't have the amount. What they want us to determine is the pressure. In order to determine the pressure, I need the volume, which I have. I need the temperature, which I have, but I don't have the amount. I don't have the amount. But they're telling us it's a helium-filled balloon. And so if we know it's helium, then I know the molar mass of helium. The molar mass of helium is equal to 4.002
261.
grams per mole.
We rounded 4.003 then.
Yes.
3 or 4 seconds.
Okay. So there are different ways we could do this. One, we could have certain equations memorized. So for example, if I have the equations memorized, I would say, okay, the molar mass is equal to the density. I'm not given the density here, but I could figure out the density. How can I get the density? I take the grams divided by the liters. That's the density. Or I could just leave it. This is equal to the mass times what? RT divided by PV.
But we already know what the density is. Or we can figure it out.
We could figure it out, but I'm not. I'm just going to plug in the mass, 1.0 grams. R is going to be 0.08206 liters times atmosphere divided by mole Kelvin. T is the temperature in Kelvin. 273 plus 22 is 298.5 Kelvin. Divided by P, which we're solving for, that's our unknown, divided by V, 0.77 liters. And the molar mass is 4.002 grams per mole.
What's next to 0.0826?
Liters times atmosphere divided by mole Kelvin. So we just got to make sure the units work out. So the grams cancel out the grams, the moles cancel out the moles, the Kelvin cancels out, the liters cancel out, and that leaves me with just the units of atmosphere. Do you see that? I don't want to memorize a whole bunch of variations of equations. The other approach you could do is you could do what's called the dimensional analysis approach. Let's say I don't like memorizing equations, or I forgot the equation. I forgot the equation and I forgot how to derive it. Then we could still solve this problem. The pressure is our unknown. The volume was 0.77 liters, and we didn't know, and T we knew as 295 Kelvin or 22 degrees C. The additional information they gave us was helium. Helium is 4.002 grams per mole. And so what I need is I need P. I'm trying to solve for P. What are the units of P? Units of P are in atmospheres. And what has atmospheres on the top? Well, 0.08206 does. It has liters times atmosphere divided by mole Kelvin. So,
Where do we get that number from? 0.046?
you memorize it. How many of these R's do you want to memorize? Not a lot. What you want to do is you just want to memorize one. Your book will have you memorize 2 or 3.
Memorize one for after this.
Yeah, memorize one and then figure out, just change the units. So if we want atmospheres, what do we have to get rid of? We have to get rid of liters, we have to get rid of moles, and Kelvin. Getting rid of liters is easy. You know how I can get rid of liters? Yeah, I'm just going to divide by volume. So I'm just going to multiply by the conversion factor of my volume. My volume is what?
0.6.
Yeah, or just divide by volume, 0.77 liters. If I do that, then the liters cancel. Okay, what else can I cancel? Yeah, the Kelvin should be easy to cancel. I'm just going to multiply by 295 Kelvin. And so the Kelvin, cancel out the Kelvin. But I need to get rid of moles, but oh yeah, I'm going to use helium here. And so I'm just going to flip this over. 1 mole weighs 4.002 grams.
We also get a
Yeah, so I'm going to get rid of my moles here. But now I got to get rid of grams. How can I get rid of grams? Well, in the problem, what did they give us?
1.0.
They gave us 1.0 grams. So fortunately, I can get rid of grams because I have 1.0 grams of helium. And so the grams cancel out. And I'm left with atmospheres. So in this particular case, I didn't have to memorize any equation. I'm just using dimensional analysis. Dimensional analysis is just trying to get rid of the units. So let's see what I get. 0.08206 divided by 0.77 times 295 divided by 4.002 times 1. And I get 7.85 atmospheres. I'm only allowed 2 sig figs, so we'll round that to 7.9 atmospheres. Let's see what they got. They got 7.9 atmospheres. So in this case, I didn't have to memorize any equation. I just figured it out using.
Atmospheres, what is that?
It's the pressure of the helium.
Okay, atmospheric pressure.
7.9 atmospheres of helium gas inside some container. So if you had a container of helium, and you'd have about 8 atmospheres of helium in here. What's atmospheric pressure outside this container? We have about 1 atmosphere outside. So if you open the valve here, helium will escape out. When the tank pressure goes to 1 atmosphere of helium, will any helium be forced out? No. Essentially, it'd be empty.
How do you increase the pressure? Just set it?
How you increase there? You can heat it up. That's one way. Or you can just add more moles of helium gas in there. And so you compress it in and force more moles of helium in there. That'll increase the pressure. Because the pressure is going to be directly proportional to the number of moles of gas. And so when you buy a tank of helium, you don't want to buy an empty tank. You'll not be able to fill any balloons with it. And so the pressure on the tank is directly proportional to the number of moles of gas you have in there. So the higher the pressure, the more. Normally when we buy, you know how many how many PSI we usually buy. Our tanks are about 2,300 PSI. So 2,300 divided by 15, let's say, is 20 atmospheres. We usually buy, that would be a brand new tank of helium gas, would be about 20 atmospheres. That's in the lab. If you go for a balloon, you aren't going to get the high pressure. 14.7 pounds per square inch. Yeah. Pounds per square inch is an atmosphere. I just rounded it, right? Okay, we could do the same thing for the density. We saw that the density is related to the molar mass. We could derive this equation easily. I don't do it this way here. I do it the same way we did for the molar mass. Oh, I forgot to put the title in. The density is defined as what? The mass
over
volume. We could leave it like this. So for example, if we have the mass, we plug it in here. If we have the volume, we plug it in here. Or we could look for other relationships. The other relationship would be this. They're using capital D for the density, which is fine. We'll just use that. It's mass over volume. But using the ideal gas law, the volume is equal to nRT divided by P. And so we'll just substitute that in here. So we got the mass divided by nRT divided by P.
Mass times P.
Yeah, so it's going to be mass times P divided by nRT. This looks even worse. This looks a lot better. But one thing that makes this much better is mass over N. Do you know what mass over N is called? The molar mass. And so we end up with this very simple equation. The density is equal to the molar mass times P divided by RT. So this allows us to calculate the density of any gas at any pressure and any temperature. We don't have to measure anything. Of any gas. Any gas at a given pressure and temperature. We could also do this using dimensional analysis. I mean, we don't have to memorize the equation. So this is the equation here. Density is equal to the molar mass times P divided by RT. So we know the molar mass of helium. Here's the temperature, here's the pressure. That's it. So the molar mass of helium, they use 4.003. Okay, this is a different R. Do you see they're using 62.4? The reason is because they're using torr instead of atmospheres. Do you want to memorize this? No. But if you already have it memorized, that's fine.
So for atmosphere pressure is 0.0806, and for torr it's 62.4.
Yeah, so what I would do here is I wouldn't even bother with this. What I would do here is I would convert torr into atmospheres. So we know that 1 atmosphere is equivalent to 760 torr. And so I would go 744 divided by 760. 0.9789 atmospheres. Yeah, I'd plug that in. And so my calculation would be 4.002 since we use that, grams per mole. times the pressure, 0.9789. Atmospheres divided by R is 0.08206 liters times atmosphere per mole Kelvin times T. T would be 295 Kelvin. Just make sure the units work out. And so the moles cancel. The grams, actually grams don't cancel. What cancels here? Atmospheres cancel. Kelvin cancels. And that leaves me with grams per liter. Well, grams per liter is what we want. And so we'd end up with 0.162. Let's see if we get the same. So 4.002 times 0.9789 divided by 0.08206 divided by 295. And I get 0.1618. 0.1618 grams per liter, which is to 3 sig figs going to round to 0.162 grams per liter, which is the same as they got. Let's say I forgot the equation or I forgot how to derive it. Could you use dimensional analysis to figure this out? And the answer is yes, you could use dimensional analysis with the data that's given. And so let's see what was the data that was given. So if we use dimensional analysis, the data that was given is the pressure, .9789, is it? Yeah, 0.9789. Technically, we're only allowed 3 sig figs. I'm going to carry a fourth. So 9789 atmospheres. The volume, did they give us the volume? No. They didn't give us the volume. Did they give us the number of moles? No. They give us the pressure, 295 Kelvin. They didn't give us that. But they gave us some additional information, 4.002 grams per mole for helium. They gave us that. And so what we want is we want grams per liter. That's the density of a gas. Gases are a lot less dense, so it's grams per liter rather than grams per milliliter. And so I need grams on top. Well, this has grams on top. So let's put that on top here, 4.002 grams per mole. And I need liters on the bottom. Do I have liters? No, I don't have liters. However, if I use R, I'll have liters. Because remember, R is 0.08206 liters times atmosphere per mole Kelvin. Well, this is convenient because if you look at the moles cancel. Here. So I want to leave grams per liter here. What else do I need to cancel? I need to cancel the Kelvin. So I'm going to put that in the denominator here. I'm going to put in 295 Kelvin down here. So the Kelvin cancels. And I need to cancel out one more thing.
Atmosphere.
I need to cancel out atmospheres. And that will cancel out atmospheres if I put pressure on the top. Now I'm left with just grams per liter. Let's see, the previous answer was 0.1618. Let's see, we get the same. 4.002 times 0.9789 divided by 0.08206 divided by 295. And then we get the same. This is helium. Gas. So if you forget the equation here, although this is a very common equation that people memorize there, you don't have to give up. If you forget the equation and forget how to derive the equation, we could just use straight dimensional analysis to answer this particular problem. So density is mass over volume. Molar mass is mass over moles. And then we have a new one called molar volume. Molar volume is volume per liter, or actually not volume per liter, volume per mole. In other words, the units for molar volume are going to be liters per mole. Liters per mole are the units. So this is kind of the way I would derive it here, but they did it in one step. I'll do it in a couple of steps here. So we want volume per mole, like this. And what I'm going to do is, if I have volume per mole, then what I'm going to do is I'm going to substitute N for this. I substitute it differently. I would just do this. I would put volume on the top, and then I'll just do this. N is equal to PV over RT. And then I'm going to substitute this on the bottom. So I'll put PV over RT. And the volumes cancel out. And I'll invert and multiply. I'll get RT over P. And so I could derive it in exactly the same way. And so the molar volume, this is equal to MV. Stands for the molar volume. MV. MV equals RT over P. This one most people just memorize this equation because we have to calculate this quite frequently. And so the molar volume is just equal to RT over P. So we just need R, which we have memorized, T, and the pressure. So at a common reference, calculate the molar volume at temperature of 0 degrees C. This is called STP. STP stands for standard temperature and pressure. Standard temperature is 0 degrees C, or 273 Kelvin. And standard pressure is 1 bar. This is the new standard. Do you know what the old standard is for pressure? Yeah. One atmosphere, exactly.
Why did they change it? For now and then, you change something for now and then.
They changed it because they want America to be like the rest of the world. But sometimes America is right in the sense that atmospheres are more convenient because what's normal pressure? Normal pressure is not 1 bar. Normal pressure is 1 atmosphere. So if we're working under normal conditions, we have to convert everything from bar to atmosphere, or we have to memorize normal pressure in bar. Normal pressure in bar is 0.9, what was it, 0.9 something something. I don't have it memorized. But it's a lot less convenient.
American reference.
Yeah. So metric is always good. I like metric system better. But there it's not. I think the imperial units are a lot less convenient. There it's not so good. But in this case, I like atmospheres more. We'll take a break here and then start up again. There are 2 problems I gave everybody 2 points for. So number 40, I think, and 1 other problem. And so I adjusted the multiple choice score. I was going to put a bonus question on this test. I forgot to. I was going to write it on the board. So what I'll do is I'll throw on a bonus quiz that we'll have. But I was going to do the bonus quiz today, but there's so many people absent. I'll probably do the bonus quiz tomorrow. That way I don't have to get a whole bunch of off-sequence quizzes. For the nomenclature, when do you want to do that for the retake? Well, the way the retake is going to work is it's just going to be for the ones you got wrong. So you need to study the ones that you got wrong. If you get them correct, then I'll give you like 65%, 0.65 for the nomenclature. So let's say you miss 5 of them. Then on the retake, you just do those 5. You wouldn't do the whole thing over again. Or let's say you missed all of them. If you missed all of them, then you would redo all of them.
We should do it next week.
Next week?
Yeah.
Is that enough time?
I need time to study, and not like,
Yeah.
Can we like go over it to see like the common things that they all got wrong?
You can just look it up. I mean, the names are, yeah, online. There wasn't a common thing that people got wrong. It's just they just didn't know what the formula was. If they knew what the formula was, then. But
What about like quizzes that we've done on the cards?
yeah, I'll get those back to you too. Yeah, I mean, you could retake those, as well. But eventually, everybody should get 4% on those.
I didn't get my like actual test back. I got back this week.
Oh yeah. Okay. I'll give you your actual test.
So 65 is passing me.
Yeah, the cumulative percentage. So your total percentage at 65. This,
I'm just curious, are we supposed to know which ones we got wrong and tell you, or do you have those?
did you get it back?
I got it back, I had it attached to my flashcards, but it's gone, so I'm.
Yeah, you're supposed to tell me which ones you got wrong, and if you don't remember it, then you have to take a look. Actually, the easiest is if you hand back. Just look for it, and then hand back both your old nomenclature test and your new one, and then I can just do it easily. Hopefully, it comes up.
It's just the same questions.
Yeah. So just resubmit your old one and along with your new one when we do it. But you'll have to have them memorized because it's going to be closed book, closed notes.
Did I resubmit this?
Yeah, but give it to me tomorrow. Okay, were there any other questions? Uh-huh.
What labs are due and when?
The lab, the equation writing was already due, but I didn't collect it. The equations were the reactions that we did, and you had to write
Where do we get those in?
you could turn them in tomorrow. Yeah. The equations that you had to write the CE, the IE, and the NIE for. Remember those? That'll be due. The next experiment that's due is experiment 10, but there were some questions about the calculation, so I could talk about that, and you can turn that in later. The drawing lab, a lot of people didn't get very far on that particular one. Some people finished it, but I had a huge range, you know, from the people who finished to the people who did none, got 0. And so, what we'll have you do with that one is to turn it in with just the drawings. You don't have to show me the models. We'll have that due next week. So let's have experiment 10 and experiment 8 due next week. And then we'll do the equations tomorrow. Okay.
Experiment 10 is like the acetic acid stuff, right?
Right, the acetic acid. I didn't give you the equation for the last calculation. I was going to have you figure it out, but
On Wednesday, they do, right?
yeah. Again, you know, this week I'm going to be gone Wednesday and I'm going to be gone Monday of next week. So Tuesday, I normally do.
Class for those days?
Yeah, just video. But you don't have to come to class. I won't be here.
Is it Zoom or just recording?
I'm thinking just recording, but yeah.
Going out of town?
Yeah, I have to go out of town, so that's why. Wednesday. I'll announce it again tomorrow. Wednesday and Monday.
The next
I'm going to Oregon. What's that?
It's 10 to 2 weeks.
Yeah. The next exam is going to be in 3 weeks
That's the final?
or 2 weeks. Is the next exam in 2 weeks? Exam 4?
Exam 4 and exam
Yeah. All right, and then the final in 3 weeks.
Not the final?
No, you're going to have exam 4 and then the final the following week. So it's in 2 weeks. So next week we should do the nomenclature retake, I think.
Good time to start reviewing the material.
Yeah, it's a good time to start reviewing the material.
Are you going hiking in Oregon? Or rock climbing?
No. There's a big race there, so that's where I'm going. We'll just finish up this chapter here and then start the next one. So this is memorized or derived or what's another way of getting this equation? So this is molar volume. If you know the molar volume is liters per mole, then we can figure it out. There's another way of deriving this. And so I showed you one way on the previous slide, did I?
It was the, what's it called? Conventional analysis.
Yeah, I showed you one way of deriving this here. But there's actually easier ways of deriving this. And so let's do some other ways of looking at this. And one way of doing that is by rearranging the ideal gas equation. And so this is probably the easiest way of doing it. And so what you do is you divide both sides by P and divide both sides by N. And so what we end up with is V over N is equal to RT over P. Or we could use dimensional analysis. And so this is just algebra here with no substitution. For dimensional analysis, we want the units liters per mole. And so we have to figure out, how do we get liters on the top? Well, to get liters on the top, we typically want the volume to be on the top. And the number of moles, then we want N to be on the bottom. But what we're going to do is we're going to do R here. R is going to be 0.08206 liters times atmosphere per mole Kelvin. And then what we have to do is we have to get rid of atmospheres. So we have to divide by the pressure in atmospheres. And then we'll get rid of the atmospheres. And then we have to get rid of Kelvin. So we'll multiply by the temperature in Kelvin. And that would give us that. And so we could use dimensional analysis as well to figure this out. But going back to this previous slide, we were talking about the molar volume with the new standard. The new standard is 1 bar. The old standard, this is the old one. This is the molar volume at STP new. This is the molar volume at STP old. And so when I was in Chem 4 and high school Chem, I had to memorize this, 22.4 liters per mole. And so I've had that memorized for a long time now. There are 22.4 liters, about this much. 22.4 liters for every mole of gas. That's how much volume it takes. So I memorized that many, many, many years ago, but how many times have I used it since then? Not a lot, 0.
Beauty of education.
So I thought, what was the purpose of memorizing this? And so a lot of people will have you memorize the new one. The new one's 22.7. Why? Oh, you know what? I got it mixed up.
The old is really
No, the old one's 22.4. The new one's 22.7. It's bigger volume because 1 bar is smaller than 1 atmosphere. It's like 0.99 something bar. Or no, wait a minute. 1 bar is 1 bar is smaller, so it's 0.99 atmospheres or something per bar. So 1 bar is a little bit bigger. Yeah, and so 1 bar is a little bit lower pressure. A little bit lower pressure is a bigger volume. And so, no, 1 bar is smaller than 1 atmosphere. So volume is bigger. You know, the volume grows bigger at lower pressure. And in fact, what we can do here is we can tell you what it is. It's 1.01325 bar is equivalent to 1 atmosphere. And so the bar is a little bit smaller than the atmosphere. All right, so what we use the molar volume mostly for. What we use molar volume for mostly is gas stoichiometry. There are different ways that we can do gas stoichiometry. The easiest is to do a liter-to-liter conversion using Avogadro's law. But if we don't do that, we can also do it this way too. So for example, if we have the pressure, volume, and temperature of a gas, then we can calculate the moles. The only thing that's missing is N. So we use the ideal gas law here as option 1, or option 2, we use the molar volume of the gas. And so we'll just look at this part right here of the stoichiometry map. And so option 1 is to use PV equals nRT, or option 2 is to use the molar volume. And the same thing goes over here. When we have the moles and we want to get the pressure, volume, or temperature, then option 1 is to use the ideal gas law, PV equals nRT, or option 2, we can use the molar volume. And so this is why a lot of people will have the molar volume equation memorized. And then there's one more option. One more option is if we have liters. We can do a liter to liter conversion and bypass moles altogether. Liter to liter conversion. So let's look at this example problem they give here. In this case, we can't do a liter to liter conversion because zinc is a solid, HCl is aqueous, hydrogen's a gas, zinc chloride's aqueous. If they're all gases, or if the ones that we were interested in were gases, then we'd be okay to do a liter to liter. But in this case, what volume of hydrogen measured at STP can be released by 42.7 grams of zinc as it reacts with hydrochloric acid? STP is not very useful. So I'm going to change this problem. I'm not going to make you memorize the molar volume of a gas at STP. What does STP mean?
No, sorry, what is the molar volume?
Molar volume of a gas at STP, 22.4 liters old, 22.7 liters new. Unfortunately, I have those memorized, but I'm not going to use them. So what we're going to do is we're going to redo this problem here. But we're going to change it from STP to RTP. I'm gonna call RTP is not really used that much, I think. I'm gonna call RTP room temperature and pressure. What's normal room temperature? What is it? 32 Celsius is awfully hot. 32 Celsius. Huh? Actually, it is about 77 Fahrenheit, which is 25 degrees Celsius, 298 Kelvin. What is room pressure? 14.7 psi, or 1 atmosphere. Let's go with that. The reason is because STP is 0 degrees C. Do you work at 0 degrees C much? No.
On the exam, we're going to want to use STP or RTP.
RTP. What is the molar volume of gas at RTP? And so let's calculate the molar volume at RTP. The molar volume at RTP is going to equal RT divided by P. R is 0.08206 liters times atmosphere per mole Kelvin. T is 298.15 Kelvin. P is just 1 atmosphere. We're going to say exactly 1 atmosphere. And so let's go ahead and calculate RT over P, which is the molar volume.
Why is it 0.15 Kelvin?
I want more sig figs, that's all. It depends on how many sig figs you want. 0.08206 times 298.15. $24.466. Liters per mole, which is 24.47 liters per mole, or 24.5 liters per mole, or 25 liters per mole. Depends on how precise you want to be. And so under standard, oops, I don't know if that's easy to see. Yeah. Uh-huh. So a mole of gas is about 25 liters under normal room conditions. 2 moles of gas would be about 50 liters. 3 moles of gas would be about 75 liters. Depending on how precise we need to be. And so let's go ahead and do this particular problem here. So we're going to just do this. We're going to go from grams of zinc to moles of zinc. And then from moles of zinc, we'll go to moles of hydrogen. And from moles of hydrogen, we'll go to volume of hydrogen.
Not grams.
No, not grams, because they're asking what volume here. And so we're not going to go to grams. Okay, so we're starting off with 42.7 grams of zinc. And then we need the molar mass of zinc, 63 point, or actually, what do you see, 65? 65.39? Thanks. So grams of zinc cancels. And then from moles of zinc to moles of hydrogen, it's a 1-to-1 mole ratio. So 1 mole of hydrogen for every 1 mole of zinc. Moles of zinc cancel, moles of hydrogen. Okay, here is, I'm going to use the molar volume method. There are 24.5 0.47 liters per mole of gas at RTP. And so the moles cancel, and that leaves me with liters of hydrogen gas. So we'll go 42.7 divided by 65.39 times 24.47. 15.979 liters. We're allowed 3 sig figs, so this is going to be 16.0 liters of hydrogen gas. This is the molar volume method. Alternatively, we could do the PV equals nRT method. The PV equals nRT, we do this, 42.7 grams of zinc, and then convert that to moles of zinc. And then convert that to moles of hydrogen. And then stop. So I would have 42.7 divided by 65.39. And that gives me 0.6530 moles of zinc, which is the same as the moles of hydrogen. So I'll have 0.6530 moles of hydrogen. And then I'm going to plug that into the ideal gas law. V is equal to nRT over P. And then I have 0.653 moles of hydrogen times R, 0.08206 liters times atmosphere per mole times Kelvin times T. T, I'm using 298.15 Kelvin. And P is exactly 1 atmosphere, so infinite sig figs there. And I will get 15.979 liters, which is going to be 16.0 liters of hydrogen gas. I get the same answer. So here, it's useful to know the molar volume at room temperature and pressure, because most of the problems that we do are room temperature and pressure, room pressure. And so it'd be worth memorizing. It saves you a little bit of time. Not huge, so if you don't memorize it, it's fine. You can always derive it. So here they're talking about using the molar volume method, except their molar volume is different. Well, in this case, we can't use RTP because what is the pressure? 744 torr. And what is it, the temperature? 131 Celsius. So we'd have to calculate a new molar volume. So this is a handy equation to memorize. Molar volume is equal to RT over P, or derive. It's actually pretty easy to derive because we know this is V over N. And so they calculate using their R. They have a bunch of R's. All right. And so they get this. And so they just use this as a conversion factor in the stoichiometry map. And the conversion is for this, going from moles of CO2 gas to liters of CO2 gas. For any gas, it doesn't have to be CO2. We have 33.9 liters per mole under these conditions of temperature and pressure. It's quite a bit bigger than normal because the pressure is lower and the temperature is higher. That would be for the final conversion here. The other option is to stop, calculate the N, and then use PV equals nRT to solve for the volume. And so they do that here. They use the molar volume as a conversion factor. So that's the final step that they did here. You make sure. This, yes. The final step here. So they're left with moles of CO2 converted to liters using the molar volume. Alternatively, we could have stopped at moles and then used the ideal gas law. So they're just repeating the same calculation, stopping, calculating the moles, and then using the ideal gas law to calculate the volume. So here, they'll stop at moles of CO2, and then use PV equals nRT. I don't know what they're doing there, but here we use it. And so stop at moles, 1.11 moles of CO2, and then calculate V using nRT over P. There are values, so this is 62.4. We don't typically use that. I don't typically use that. He seems to use it a lot. The other way of doing stoichiometry is doing direct volume to volume conversion. And this is easiest if your temperature and pressures don't change. So if I look at this equation, this is a solid, so we ignore it. This is a gas, so we factor that in. And so if you have 1 liter of O2, how many liters of SO2 will you generate? 1. It's the same. It's a 1-to-1 mole ratio, which means it's a 1-to-1 volume ratio. So it would be a 1-to-1 volume ratio if the temperature and pressure do not change. But in this particular problem, the temperature and pressure do change. And so it screws things up. If the temperature and pressure do change, then there are other ways we could do it. That is, we could just do this regular stoichiometry the long way. Or we could do a shortcut. And what they're doing is a shortcut here. So in this shortcut method, what they say is this. They either convert the first volume to the conditions of temperature and pressure of the second, or they use the first volume and then figure out what the second volume should be and then convert that using the combined gas law. And so we can look at it here. I would do it. I wouldn't do this problem the way they did it. I'd probably do it a different way. But they have 1.75 liters of O2 at 24 degrees C and 755 torr. And then they want to convert it to 165 degrees C and 785 torr. So they're going to change the conditions here. And so we could do it in different ways. One is we could just get the conditions to match here. Which way did they do it? Let's see. I don't know which way they did it. Okay, so what they're doing here is they're going like this. 1.75 liters of O2 should produce how many liters of SO2? Now, we have T1 and P1. And so at T1 and P1. Okay, so what we're going to do is we're going to make this at T1 and P1. If the temperature and pressure do not change, then we can use Avogadro's law. And so using Avogadro's law, 1.75 liters of O2, the liter ratio is 1 to 1. So if we get 1 liter of SO2 for every 1 liter of O2. It's a 1-to-1 mole ratio, it's a 1-to-1 volume ratio. And so this is going to give me 1.75 liters of SO2 at T1 and P1. Okay, then in the next step, what they're gonna do is they're gonna change it to T2 and P2 by using the combined gas law. So what they're gonna do is they're gonna go P1V1 over N1T1 is equal to P2V2 over N2T2. Now N doesn't change, the number of moles, and so N is constant. If N's constant, it cancels out, so we're left with P1 P1V1 over T1 is equal to P2V2 over T2. Okay, now we'll want the V2. So V2 under the new conditions is equal to P1 over P2 times T2 over T1 times V1. And so they just plug it in, you know. This is T1, P1, this is T2, P2. So we just change the volume for the new conditions. So that's what they did here. And they get this. So they use the volume ratio. So 1 liter of O2 gives 1 liter of SO2. They did it kind of weird here. But this is normal. 2.48 liters, was that the right number? No, they had 1.75 liters. Oh, I see what they did. What they did was they calculated the end. So they got 2.48 liters of O2 under the new conditions. And then they said it's 1-to-1 here. Whereas I converted it initially using the volume ratio and then changed the temperature and pressure. So whether you do part 1 first or part 2 first, it doesn't matter. And so I would have gotten the same answer. Let's see. So what I did was I went ahead and used the stoichiometry to figure out how much SO2 and then change the volume of SO2 to the new temperature and pressure. What they did was they started off with the O2 and then changed the O2 to the new temperature and pressure, which gave 2 point whatever. And then they used the stoichiometry. It's a 1-to-1 liter volume ratio. And so we would have ended up with the same answer. So when I calculated V2, I would have gotten the same for that. All right, so this is an example of gas-to-gas stoichiometry problem. There are other examples of gas-to-gas stoichiometry as well. That's actually all of chapter 14. All of chapter 14. Let's take a look at chapter 15 next. Chapter 15 deals with gases, liquids, and solids. So we just talked about gases now. We're going to look at different aspects of gases here. This is a gas mixture. Dalton's law of gas mixtures. So we'll talk about that next. I'm going to start off talking about it here. 3+ ways of visualizing a gas mixture. Three plus ways, because I'm going to talk about three, but there are more than 3 ways of visualizing gas mixture. Number 1 is the mole fraction. How do we convert a fraction into a percentage? Let's say I have a mole fraction of 1/2. If you have a mole fraction of 1/2, then to convert it into a percentage, what would you do? This is multiply. Multiply by 100%. Mole fraction or percent? What's that?
In Kelvin, because something just go wrong with that percent of it. You don't need to convert.
Yeah. So let's look at air. I'm going to look at 100 moles of air. And air is going to consist of about 21 moles of O2 and about, let's say, I'm just going to go 79 moles of N2. So it's about 80% nitrogen and 20% oxygen. So the mole fraction is 21 moles of O2 per 100 moles of air. Or 21% O2. And the mole fraction of nitrogen is 79 moles of nitrogen per 100 moles of air. Or 79% nitrogen. We could do it by particles as well. You know, if I had 100 molecules, rather than 100 moles, then 21 of those molecules will be oxygen, 79 of the molecules should be nitrogen, according to the composition of air. The mass percentage is a little bit different, you know. Is, a mole of oxygen weighs 32 grams, and a mole of nitrogen weighs 28 grams. So nitrogen's a little lighter. And so the mass percentage is more like, since oxygen is heavier, it's more like 23% oxygen. It's heavier, so the greater percentage of the mass will be oxygen. This doesn't change with temperature and pressure. It's always valid, let's say. Two, we're going to look at the pressure fraction. Let's say I have air, and let's make it 1 atmosphere of air. Then I'm going to have oxygen. Oxygen's usually given red. And I'm going to have nitrogen. I'll make blue. So let's say I have 100 molecules of each. Then the pressure is generated when the molecules collide with the walls of the container. So we'll have the oxygens collide here. Actually, let's make this lack the collisions. And we'll have the nitrogens collide here. So out of these collisions, how many are generated by the nitrogen? How many are generated by the oxygen?
79%.
Yeah, 79% of the collisions are nitrogen and 21% are from the oxygen. And therefore, this is going to equal, well, what's 21% of one atmosphere?
One atmosphere is 0.72.
It would be 0.21 atmospheres of oxygen plus 0.79 atmospheres of nitrogen. And this is what we call Dalton's law. Dalton's law says that P total is equal to the sum of the partial pressures. So it's going to be PA plus PB plus dot dot dot. And so if I only have two things here, oxygen and nitrogen, then P total, in this case is 1 atmosphere, is going to equal 0.21 atmospheres of oxygen plus 0.79 atmospheres of nitrogen. And so what we can show is it visually like this. The total is going to have all of them collide. The reds and the blues. Now I'm going to remove all the blue ones. So I just have the red ones collide. If I just have the red ones collide, there are going to be a lot fewer collisions because I don't have as many reds. And therefore the pressure drops to 0.21 atmospheres. And then I'm going to have the blue ones and remove the red ones. The pressure is going to be higher because I have a lot more blues, but not as high as the total, because in the total I have both colliding with the walls, the red and the blues. So what we say here is at constant volume, which means that V total is equal to V of the oxygen, which is equal to V of the nitrogen. So let's say I had 1 liter of oxygen. And so this is kind of weird. 1 liter of oxygen plus 1 liter of nitrogen makes how many total liters? 1. Yeah. And so 1 liter of mixture.
That makes sense.
Does it make sense? Okay. If that makes sense, then you're good. Because we're just going to put everything into 1 liter box. And so here we separated that. And so this is what we mean by constant volume. The volume doesn't change, everything. And the volumes aren't additive, you know. Whereas the pressures are additive. And so over here, It's the pressure of the oxygen plus the pressure of the nitrogen is going to make the pressure total. That is, I have to account for the collisions of the red and the collisions of the blue in the total. So that's what we call pressure fraction, or Dalton's law. I should say pressure fraction or percent. %21 of the pressure is generated by the oxygen. 80 or 79, or about 80% is generated by the nitrogen. The other way of looking at this is via volume fraction or percent. I'm going to take that exact same mixture. We're going to take 1 atmosphere of air in a 1 liter box. And that 1 liter of air is going to contain nitrogen, mostly nitrogen, 80% nitrogen, and about 20% oxygen. And then what we're going to do is we're going to remove that oxygen, but we're not going to keep the volume the same. What we're going to do is we're going to reduce the volume here. We're going to reduce the volume such that the pressure doesn't change. That is, I get the same number of collisions total against the walls. So what we're going to do is we're going to compress the oxygen into a smaller box. So what we end up with is 1 liter of oxygen. So this is 1 liter of air, 1 atmosphere of air. This is going to be 1 atmosphere of oxygen. That is, we'll get the same number of collisions per unit area. And the volume is going to be different, though. The volume has to shrink down to 0.21 liters of oxygen. If I want the same pressure. Then I'm going to do the exact same thing for the nitrogen. Get this to work. So this is going to be plus, okay, I'm going to get 1 atmosphere of nitrogen. And so what I got to do is I got to have just the right size box so I get the same number of collisions per unit area. And so we end up with 1 atmosphere of nitrogen. But the box is going to be a little bit bigger because there's more nitrogen, but not as big as 1 liter. And so the box size is going to be 0.79 liters.
The box size or
Yeah.
volume?
Oh, sorry, volume. And so we see that this is going to be at constant pressure. It should have been 1 atmosphere over here of air. At constant pressure. That is, the pressure of the air is equal to the pressure of the nitrogen plus the pressure of the oxygen. Doesn't matter which order you write this in. So, for example, if I have 1 atmosphere of oxygen plus 1 atmosphere of nitrogen, how many atmospheres of air do I get? Yeah. In this case, I end up with 1 atmosphere of air. And so that's what we call constant pressure. The pressure doesn't change. However, the volume does change. And so it turns out the volume of air is equal to the volume of nitrogen plus the volume of oxygen. And so this would be 0.21 liters here. This would be 0.79 liters here. And that gives me 1 liter of air. And so the volumes are additive. And so there's different ways of visualizing the air in this room. So for example, the air in this room I can keep in the same size box or the same size container, and then I can just visualize, 80% of the molecules in this room are nitrogen, and those nitrogens are striking the wall. So if I ignore the oxygen's contribution to pressure, the pressure is going to be lower. And so let's say the room pressure right now is 1 atmosphere. That means the nitrogen in air is 80% of that, and therefore 80% of the pressure is generated by the collisions of the nitrogen. And so the pressure of the nitrogen in this room is 0.8 atmospheres. And the same thing, the pressure of the oxygen is 0.2 atmospheres. It's about 20%. But the volume of nitrogen is the same as the volume of the air. It's this whole room. And the volume of the oxygen is the same. The oxygen can go anywhere in this room it wants. That's one way. That's called Dalton's. And so we could visualize a gas mixture using Dalton's. Or we could visualize the gas mixture using Avogadro's. If I think about Avogadro's, then I think about it totally different. But it's the exact same mixture. If I think about the air in this room, what I do is I push all the oxygens to one side of the room. If I put all the oxygens to one side of the room and then make it have the same, density, that is, not density, because density depends on mass, make it have the same population per unit volume, then how much of the room would it occupy? If I push all the oxygen to this side of the room, it would only occupy about 20%. And then I push all the nitrogen to the other side of the room, that would occupy 80%. Yeah, you die on that side of the room. But basically, so those are the two ways of visualizing a gas mixture like air, by Dalton's and Avogadro's. In this chapter, we talk about Dalton. And so in terms of Dalton's, the total pressure is just equal to the sum of what we call the partial pressures. Partial pressure is a pressure of oxygen, pressure of nitrogen, since there's no third gas. If there was a third gas, we'd add that in there too. There is a third gas in air, but I ignored it because it's kind of small.
Where's the third element?
Third gas? It'd be the CO2. And a fourth gas and a fifth gas. Depends on, water's in there as well. So Dalton's law problem in Chem 4 is very simple. This is all you have to do. We have a nitrogen-oxygen mixture, and we want to figure out a nitrogen, oxygen, and argon and water mixture. We want to figure out the total pressure. So we add up the pressure of the nitrogen plus the pressure of the oxygen plus the pressure of the argon and the pressure of the water. And that gives us the total pressure there.
So not bar, right? It's not-
They're doing it in bar, so if they measure it in bar, just keep it in bar. Here's another one. So the volume's roughly the same, 1 liter, 1 liter, 1 liter. Not exactly, because there's some variation here, and so that leads to a little bit of error, but it's all right. So they're taking 186 millimeters of mercury of nitrogen, 93 millimeters of mercury of oxygen, and the total is going to be just the sum of the two. So this would be 186 plus 93 gives us 279. So the mixture is going to have that pressure. And so the mixtures are going to be the sum of the total pressure. I mean, the sum of the partial pressures, excuse me. One of the most common applications of Dalton's law is collecting gases over water. When you collect gas over water like that, you saturate the gas with humidity. And so this oxygen here is at 100% relative humidity. And so the pressure that we generate inside the container isn't all due to oxygen. The pressure we generate inside the container, the total pressure, is equal to oxygen plus the pressure of the water vapor. There's going to be humidity in here, water vapor. And so this is one of the biggest applications, collecting gases over water. And so what we say here is this: the total pressure is equal to the pressure of the gas plus the pressure of the water vapor. The pressure of the water vapor, we have tables that tell us the pressure of the water vapor. And so what we can do is we can subtract out the humidity, that is the collisions that are going to be generated by the water molecules hitting this can be subtracted out when we look at what the pressure is in a table. And the pressure of the water depends on the temperature. The higher the temperature, the more water will vaporize and the stronger the collisions you'll have.
Is it kind of empirically or?
Empirical table, exactly. It's an empirical table, so we get it out of the table. So here, we need the temperature. So given that the total pressure, so they give us the total pressure of 0.98 atmospheres, and that total pressure is the pressure of the gas plus the pressure of the water vapor, and then they give us the pressure of the water vapor at 16.5 millimeters of mercury. Normally, what they do is they give us the temperature, and we have to look up the pressure of the water vapor. And so, let's see how we do this normally. Actually, not there. Here. It's called a vapor pressure table. This is too much. This is all empirical. You can generate an empirical equation. So all we do is figure out what the temperature is, and then we could look up the vapor pressure. So let's say the temperature were 21.0, the vapor pressure would be 18.650 torr. If the pressure is 24.0, we get this, etc. And so somebody else has already measured it. And so if we want the pressure of the gas, we have to subtract out the water pressure. And so we do that, and we get this 0.96 atmosphere of oxygen. So we have some names that we put for this. What happened here? All right, the names that we put for this here are the mixture. The mixture is called wet oxygen. This is saturated with humidity. And this oxygen here is going to be called dry oxygen. This is wet oxygen. Wet oxygen is saturated with water vapor. And this is going to be at 100% relative humidity. So what that means is we can figure out how much water vapor max we can stick in air or gas at various temperatures. So 100% relative humidity. And that table I just showed in a moment ago is based on 100% relative humidity. So that's collecting gases over water. Let's take a look at some specific problems associated with that. We're running out of time. I'll look at some problems next time. Right now, what I want to do is I want to do a little bit of gas stoichiometry here. The gas stoichiometry will work except for this last one using Avogadro's relationship. That is, if I use 1 liter of methane, how many liters of oxygen do I need? 2 liters. And how many liters of CO2 will I produce? 1 liter. CO2. Let's take a look at ethane. How many CO2s will I form here? Do you know? How many O2s do I need? And how many H2O liquids will I get? And so let's balance it. I have 2 carbons here. I'll need 2 CO2s here. And I'll have 6 hydrogens over here. I'll need 3 waters here. And that gives me 2 times 2 is 4 plus 3 is 7. That means I'll have 7 halves here. Like that. But 7 halves is a bit of a pain, so I probably want to simplify that to what? Yeah. So this is what I'm going to do. I'm going to change this. I'm going to go, instead, I'm going to go with 2 ethanes, and then that's going to change to 7 O2s. This is going to change to 4 CO2s and 6 waters. Okay, I'm going to do the same thing up here. I'm going to double everything here. So if I double everything, that's going to be 2 liters here. This will be 4 liters here, and I'll get 2 liters here. Okay, so what I'm going to do is, if I take 2 liters of ethane, how many liters of CO2 do I get?
7.
4 liters of CO2. All right, now take a look at this problem here. I'm going to give you an advanced problem. And this advanced problem is going to have 2-liter mixture of ethane and methane. Was burned. And it produced three liters of CO2. What is the percent composition of the mixture? We have a couple of minutes left, so think about that. Can you tell me what the percent mixture is?
What was
Methane is CH4. 50-50. 50-50 is correct. This is a 50-50 mixture. Okay, now I'm going to, it's a 50-50 mixture. And so a 50-50 mix would be 1 liter of methane and 1 liter of ethane in a Avogadro sense. Okay, now we're going to do this again, but okay, this is 1. Let's say that instead of that, I got 2.83 liters of CO2 gas was formed from a different mixture, a different methane and ethane mixture. What is the percent comp in the mix? This is going to be your bonus question for the last test. This one we'll do tomorrow, and this is what I'm going to post for tomorrow, okay? We'll stop now.